Alright. So that's what I'm going to do. Here's Tuttle Creek outside of Manhattan. I'm going to check to see if the water is level across here. So I got the coordinates for point A. So it's 39, 15, 17.85 north and 96, 36, 16.34 west. And then I got that coordinate too. And then the length of that yellow line is 1.30 miles, which is 6,842 feet. So I'm going to check that out to see if it's level. Okay. So I guess I'm going to go into this is how I do it from the NGS site. So I'm going to use XYZ coordinates, and the Cartesian coordinates XYZ allows for the geodetic quality three-dimensional positioning on Earth centered ellipsoid. The utilities in this package provide methods for converting between geodetic latitude, longitude, ellipsoid height, and the XYZ on the GRS 80 ellipsoid. Okay, so I'm establishing this line right here, and so that'll give me the latitude, and this is the longitude. So, and how I know the elevation is from, you can use USGS or the Corps of Engineers. So I did it for 4/28/2019. So my elevation is 1116. So, and this is how I'll do it. I'll get from point A to point B. So I'll get I have my elevation. I'll get the delta elevation, the zenith elevation or angle, which is the horizontal plane. And then I'll get the reciprocal sum, the delta arc, and the miles, and the curve drop. So I'm getting a lot of info right there. All right. So I got the ellipsoid height, and I got the latitude and longitude. So this is the perfect circle, and this is the ellipsoid, which it has a major and minor axis. So that's the ellipse. And then this is like Greenwich, so these are 90 degrees. So then I'll import my file, which I already have filled out. So the reason why it popped in there into place on the surface, so if I go ID and then I hit this, it's 0, 0, 0. So that's the origin point. And so they're right here. Okay, so start off by drawing the distance. So my drawing's in meters. I need to convert it to feet or miles. And so it was 6,842. So I got 6,842.05. Perfect. Okay. We'll change that to blue or something. And now I need to draw a line to the equator. And then rotate that line to that line. And you'll notice it's right on. So when I did that, so alright, now I need to draw the angle. So now I'm drawing damn it, I got rid of it. UCS. XY. And here to here. Change that to white. And extend. And see, it doesn't hit it to the center just like that picture I showed. Alright. So that's what I just drew right there. So And that will give me the latitude. So if I go 3 point NEA to end, back to here, and measure it. And so it was 39 for 0.8, 39.15, 17.85. So that's why it rounded it to 8. Perfect. So pretty cool. And that line's a long ways. Just that line right there is probably, I couldn't even tell you, but I will. I don't know how long it is. How we do that too. Meters to feet. I need miles. So it's 3942, 3,942 miles. So, to the where this drill. Alright. Because this here ain't much, so. Anyways. Now I need to do the same thing for this side. We'll go green. Line. Down to the equator. Rotate. Reference. NEA. Here to here. Change that to green. Line. Node to node. UCF, XY, and extend. And I can extend this line too if I want. So it's a triangle now. Alright, now that I got that, now I can draw my tangent line. So now I'm going to draw the tangent line, which is the horizontal plane. So 3 point UCS, NEA, here to the node, which is the ground, or the lake water right there, and then NEA to right here. Line. So it draws two of them. I know it's that one, extend it way over. Leave it green, why not? Redo my UCS to that. NEA. And then NEA to that line. And if I measure it from here to here, it's 90 degrees backwards. So I'll get into that view. So the green line was, so there's the water, and here's my tangent line. So the drop is from here to there is meters to feet. Paste. So I got 1.12 really. Okay, so if I come over here to the Earth curve calculator, and height is 0, and we'll say 1.3 miles. We'll say calculate, and I got 1.1270 for the target hidden height. And I got 1.2. So I'm like right on. Alright. So that checks out. Now what the so now that measurement there is the delta elevation, which they'll be the same on both sides because this is an example that Jesse did. He's a geodetic surveyor, and so he has different elevations. 200s, so mine's the same. So I got 37 seconds. So and then so now I'll measure the curve delta, which is this delta arc. Yeah, it's the delta arc. So that's what I'm measuring now. 3 point and and back out to the other point B. Let me. And measure. So I got 1.7. Okay. So now I need to know. So the sum, the reciprocal sum, should match that or close to it. Okay. So I got, so for here I got 90, 0, 0, 37 plus, or enter, and 90, 0, 0, 37 plus, and then I go minus 180, 180, 0, 0, and 0, 0, minus. So I got 1 minute and 14 seconds. So I was 7 seconds off. And so then I wrote that to Jesse, and so this is what he said. Let me see here. So I go, Jesse is Chris question for Tuttle Creek. Measurements across the lake at water level at the same height. For point A, I get 90 degrees, 0 minutes and 37 seconds. And on the other side, point B, same thing. So 180, 1 minute and 14 seconds minus 180 equals 114. But my delta says 1.7. They don't match by 7 minutes. So, and then he wrote back saying, not 7 minutes. Well, yeah, I know. They agree with 7 seconds, which is excellent. So that's a good. So that's very cool, good results. So, so that's what I got. I got 1.12 of a drop of its curves. So it's not flat.